Here's another function, x cubed minus 6x squared plus 12x minus 5. And we are asked for a lot of information, critical numbers, inflection points, all this good stuff. Let's label where each one comes from. So from the first derivative is critical numbers. What else? Relative max, relative min, increasing, decreasing, all coming from our first derivative. Everything else is the second derivative, so inflection points, concave up and concave down. All right, so looking at this function, I'm going to rewrite it down here so that you can see it a little bit better. So we have f of x is x cubed minus 6x squared plus 12x minus 5. We're going to split our entire page in half so that we can do the first derivative stuff and the second derivative stuff. So split your page up. We're going to make two separate sign charts and interpret them differently. So looking at the first derivative side, the first derivative is 3x squared minus 6 times 2 is going to give us 12x, and then the derivative of 12x is 12, and then the derivative of negative 5 is 0. So here's my first derivative. I'm going to set it equal to 0, and then I'm going to have to factor this because it has an x squared. I need to factor, so I'm going to pull out a 3 because that's a GCF, and I can't pull out an x because the last term doesn't have an x on it. So I'm just going to pull out a 3 times x squared will give me 3x squared. 3 times a negative 4x will give me negative 12x. And 3 times a positive 4 will give me a positive 12 at the end. I can still continue to try to factor, so I'm going to keep the 3 and see if I can reverse FOIL this. I want to see if there is a number that will multiply to be 4 and add up to be negative 4. So do I have two positives or two negatives to multiply to be a positive but add up to be a negative? It must be two negatives will multiply to be a positive but add up to be a negative. So what are factors of 4 that add up to be 4? So negative 4 and negative 1 would be negative 5, so it must be negative 2 and negative 2. So 3 things can only multiply to be 0 if at least one of them is 0. Can we make 3 equal 0? No, 3 is always 3. There's no x there. Can you make x minus 2 equal 0? Yes, if x is positive 2. And that is actually for both of them because the next factor is x minus 2, which would only be 0 if x was positive 2. So there's only one critical number here. It just happens twice. It's called a multiplicity of 2, not anything we even use in this class. So you might remember it from algebra. It doesn't matter if you don't. Our one and only critical number is x equals 2. I don't have to check if it goes into the original because it made the derivative 0 instead of undefined. So we are good. It is a critical number for sure. The question is now, is it a relative max or min? And where are we increasing and decreasing? That all comes from our sign chart. So on my sign chart, I have one super important critical number here. It makes f prime 0. I can plug in any number I want to the left and to the right. So to the left first, I'm going to plug into the factored form. If I plug in my first factor is 3, which is positive. My second factor, 0 minus 2 is negative. My third factor, 0 minus 2, is also going to be negative. So I end up with a positive times a negative, which is going to go back and be positive. Careful on your interpretation. This is the first derivative. If it's positive, is that increasing or is it concave up? First derivative means it's increasing. After 2, we can plug in anything we want to. I've done a lot of 10, so let's plug in maybe 5. So plugging in 5 to this, I'm plugging into the factored form. My first factor is 3, which is positive. 5 minus 2 is positive. And 5 minus 2 again is positive. 3 positives will definitely make a positive, which means after the critical number, the function is still increasing. So we can draw what that looks like at the end just to get an idea for next section. But for now, I'm just going to interpret. That's a lot of work already. So we'll just stop there. We won't draw a picture. We're just going to see what we have. Is this a relative, max, min, or neither at my critical number? If it goes from increasing to increasing, no sign change means it's neither a max or a min, which I love because now we don't have to find any y values. We can just say none for these points. Our one and only critical number happens to not be a max or a min, which is perfect. Less things to plug into the original function. For increasing, I would say it's increasing before our critical number 2. So let me label these again. Negative infinity is x to the left. Positive infinity is x to the right. So before 2 and after 2, it's increasing. So in interval notation, I would say negative infinity to 2, union 2 to infinity. It's increasing everywhere except for at the x value where the derivative is 0. It's not increasing or decreasing at 2 since the derivative is 0. And then decreasing, there are none. Now we can move on to the second derivative. So I need to take the second derivative and do my same 2 steps. Well, when I look to take the second derivative, what's easier to take the second derivative of? This factored form, or the original? Let's not do a product rule if we don't have to. So I'm just going to look at this first line. This is a lot easier to take the derivative of than this crazy factored form, which is going to be too much. So my second derivative, looking at the top there, I would bring down the power. So the second derivative is 6x. Derivative of negative 12x is negative 12. Derivative of 12 at the end is 0. Oh, this is why I love second derivatives. So much nicer than the first derivative. We don't have to factor. We have a linear equation. So all I have to do is add 12. There's no x squared, which tells me you don't have to factor. So I have 6x equals 12. And then I get to divide by 6. So x equals 12 divided by 6, which is 2. Is this an inflection point? I don't know. I don't know until concavity changes. That's the second thing that makes it an inflection point. Makes the derivative 0. In this case, second derivative is 0, just fine. 6 times 2 is 12 minus 12. It definitely makes the second derivative 0, but does it have a change in concavity? Let's find out on our sign chart by doing our second step. I can pick any number before 2. I'm going to label it because it's special. It makes f double prime 0. Before 2, I like to choose 0 when I can, so I'm going to plug in 0. And I'm plugging into this derivative, which is 6 times 0 minus 12. It's not a factored form like the other one, so I actually have to think about the number I get, whether it's positive or negative. It's not just like a factor times a factor like the one before. But it's not too bad to plug into. 6 times 0 is 0. 0 minus 12 is definitely negative. Careful on your interpretation. Negative second derivative means concave down, not decreasing. That's the first derivative. I can plug in any number after. Maybe I'll plug in 5 again. So if I plug in, I have 6 times 5, which is 30. 30 minus 12 is going to be some positive number. Positive second derivative means concave up. Do we get an inflection point then? Yes. It makes the second derivative 0 and has concavity change. So it checks off the 2 things that we needed. So I have to plug in and find a y value, which is a bummer. But I'm going to go back to the original function, and I'm just going to plug in 2. So I would do 2 cubed minus 6 times 2 squared plus 12 times 2 minus 5. Plugging into the original, I get a y value of 3. So this is f of 2. Only time you ever use the original. Derivatives on sign chart, original to find a y value. Last piece, where am I concave up? So putting in my infinities here, I'm concave up after 2. So from 2 to infinity. And I'm concave down before 2. So I would say negative infinity to 2. There's our interpretation. This would be all you would need to finish a problem in this section. But next section is graphing. So if you have some space below, or in my case above, so that we could see it all at once, I'm going to try to draw what this graph looks like just to give us a preview of what it means to have something increasing and be concave down to concave up. So let's see what the graph is going to be. We want to do something that's concave down to concave up. So let's first think about concave down. It's concave down until we get to the x value 2, which has a y value 3. So here's my point 2, 3. There's my inflection point. Just putting a random point in there. And before that inflection point, I'm concave down and I'm increasing. Let's think of what that would have to look like. Concave down looks 3 different ways. Upside down U, just the left side of the upside down U, or just the right side. I want it concave down but increasing. So let's label this. This is increasing to decreasing. This one's always increasing. This one's always decreasing. So I need to choose this piece here, something that's rising left to right but oriented downward for before 2. Maybe something like that. Increasing but face down. And then after 2, I want to be concave up and increasing. Interpreting my sign charts as concave up and increasing. Let's think about what concave up would have to look like. It's a U, it's the left side of a U, or it's the right side of the U. Which one is always increasing? Which concave up is rising left to right? This one's falling, and this one's rising. So I need to connect it with the shape that looks like this. We're increasing, it kind of bottoms out at our critical number, and then we go to increasing again. So it's not a max or a min. And there we switch from being face down to being face up. There's a sketch that's super difficult, but we're going to get to the point where we can do it in the next section.